Hello, hi everyone. This is Dr. Yuragandar, Assistant Professor of Chemistry, MVS Government Degree and PG College, Mahabub Nagar. Welcome to this online video classes. Today I would like to explain part 2 of heterocyclic compound. I developed one video on heterocyclic compounds, that is part 1 of heterocyclic compounds. In part 1 of heterocyclic compound, I explained about the classification of hydrocarbons as well as classification of heterocyclic compounds, introduction, nomenclature, so many. In this video, I would like to explain the other topics of heterocyclic compounds. Okay, fine. Next. In this video, I would like to explain the importance of heterocyclic compounds in nature. I would like to explain about the simple five-membered heterocyclic compounds, that is pyrrole, furan, thiophene. In these five-membered heterocyclic compounds, I would like to explain about pyrrole in this video. In pyrrole, I would like to explain introduction of pyrrole, preparation methods, physical properties, and chemical properties of pyrrole. Okay, fine. Next. What is the importance of heterocyclic compounds? Why we should know about heterocyclic compounds? Generally, heterocyclic compounds are generally widely distributed in nature. There is a lot of heterocyclic compounds in natural products. They present in so many important natural products such as many B complex vitamins such as thiamine. Thiamine contains thiophene derivative. Vitamin B6 and niacin contains pyridine structure. Vitamin B12, that is cyanocobalamin, contains benzoimidazole structure, as well as chlorophyll, hemoglobin, both contains porphyrin rings. That is, porphyrin rings are nothing but they contain tetrapyrrole rings, as well as so many other color pigments of the plants also contains heterocyclic structures. Heterocyclic compounds also present in many antibiotics, amino acids, proteins, enzymes, and so many medicines. For example, in proline, hydroxylamine, tryptophan, in histidine, all these amino acids, generally there are some heterocyclic compounds, heterocyclic structures. In quinine drug, as well as in serotonin, melatonin, NADP enzymes also contains some heterocyclic structures. They also present in so many alkaloids. Alkaloids nothing but they are the bases, nitrogen bases, which obtains from higher plants. For example, nicotine, morphines, quinine, papaverine, caffeine, cocaine, atropine. These are example for alkaloids. All these alkaloids, that is nitrogen bases, which obtained from higher planted, generally contains one or more than one heterocyclic ring systems. They also present, that is heterocyclic structures also present in gene transferring molecules, that is DNA and RNA molecules, that is DNA RNA nucleic acids, in the form of uracil, guanine, thiamine, adenine, or cytosine. These genes generally contain pyrimidine and furin bases, which contain heterocyclic rings. Generally, many heterocyclic, that is oxygen heterocyclic compounds, generally present in carbohydrates and their carbohydrate derivatives. So there is a lot of importance for heterocyclic compound, so we should know something about heterocyclic compounds. Here, if you observe the compounds in which heterocyclic ring system presents, the main one are chlorophyll, Chlorophyll is essential for photosynthesis. Without photosynthesis, generally chlorophyll presence in leaves of the green plants, which are responsible for production of carbohydrates. Without chlorophyll, plants cannot produce carbohydrates. Alternately, no living being survive on the earth without presence of photosynthesis reaction on the earth. That is the importance of chlorophyll. Alternately, that is the importance of heterocyclic compounds. The other one is hemoglobin. Hemoglobin generally presents in animals' blood. It is essential for transferring oxygen as well as removal of carbon dioxide. So, without hemoglobin, it is impossible to transfer or to transport oxygen from lungs to various parts of the body. So, hemoglobin is essential in the sustain of living beings. So, alternately, heterocyclic compounds are very important for the survival of the life on the earth. There are also so many important compounds which have heterocyclic compounds, that is many B complex vitamins as well as many color pigments as well as so many drugs also contains heterocyclic compounds such as quinine, which is generally useful for antimalarial, used as anti-malarial drug. So many alkaloids used as antibiotics. Okay, this is something about the importance of heterocyclic compounds. Okay, fine. Next, simple five-membered heterocyclic compounds. That is the heterocyclic compounds which contains five atoms in their rings. The best examples are pyrrole, furan, thiophene, or best example for simple five-membered heterocyclic compounds. In the last video, that is the part 1 of heterocyclic compounds, I explained about the classification of heterocyclic compounds. Mainly, heterocyclic compounds classified into mm, 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 different types based on two parameters. One is based on the ring structure or ring system. The second one is based on the aromaticity. According to ring system, they classified into two types. One is simple heterocyclic compounds, that is they contains only one ring system. The other one is fused or condensed heterocyclic systems which have two or more than two ring systems. Here, the five-member heterocyclic are example for simple heterocyclic compounds. In five-membered heterocyclic compound, the best examples are pyrrole, furan, thiophene. If you observe the structures of these five-membered heterocyclic compounds, it is the first one is furan. It is a five-membered heterocyclic compound with oxygen heteroatom. The next one is pyrrole. It is also five-membered heterocyclic compound with nitrogen heteroatom. The third one is thiophene. It is also five-membered heterocyclic compound with sulfur heteroatom. The next one is the aromaticity or aromatic character of five-membered heterocycles. All the five-membered heterocyclic compounds generally shows aromaticity because they have planar structure, they have conjugated pi bonds, and also they obey Huckel's 4n plus 2 pi rule because all the pi-membered heterocyclic compounds contain two pi bonds, whether it may be furan or it may be pyrrole or it may be thiophene. All contain two pi bonds and all contains one or more than one lone pair of electrons on heteroatom. In the case of oxygen and sulfur, they contain two pairs of two lone pairs of electrons, but in the case of nitrogen it contains one lone pair of electrons. So here from the heteroatom one lone pair is conjugation with pi bond, so it undergo delocalization into the five membered ring. So then the compounds, that is heterocyclic compounds, gets resonance structures and forms a 6 5 electron aromatic sextet. So they form 6 5 electron aromatic sextate. So they shows aromaticity, that is they obey the 4n plus 2 pi rule, that is Hückel rule, due to the involvement of lone pair of heteroatom into the ring. Okay, this is due to the involvement of the lone pair of electron into the ring system, that is it undergo delocalization into the ring structure. That's why it develops various resonating structures. So orally it forms a 6 pi electron aromatic sextate and obeys the Hückel rule. So finally they shows aromatic character. If you observe the due to the resonance structures, the molecules get some energy which is nothing but resonance energy. If you observe the resonance energy of these five-membered heterocyclic compounds, that is pyrrole, furan, thiophene, their resonance energies are generally 22 kilocalorie per mole, 16 kilocalorie per mole, 30 kilocalorie per mole respectively. That is the furan contains 16 kilocalorie per mole resonance energy, pyrrole contains 22 kilocalorie per mole energy. The other one, that is thiophene, contains 30 kilocalorie per mole resonance energy. Okay, this is about the aromaticity of the five-membered heterocyclic compounds. Next, here the if you observe the resonance energy values of all the five-membered heterocyclic, they have generally less than that of the benzene compound or benzene molecule. The benzene molecule resonance energy is 36 kilocalorie per mole. Here, all the three heterocyclic compounds generally contain the resonance energy value less than that of the benzene. That is, they have generally, they may be below 36, 30, 22, 16. So, their resonance energy values are less than that of the benzene molecule. Here, there is difference in their resonance energy values for three heterocyclic compounds, that is, three five-membered heterocyclic compounds. Here, the difference for their resonance energy is it is due to the difference in the electronegativity values of the heteroatom. Due to the difference in electronegativity values of the heteroatoms, they shows difference in their resonance energies values. Here, if you observe the electronegativity values of these heteroatoms, that is nitrogen, oxygen, sulfur. Oxygen contains more electronegativity, after that nitrogen, after that the least electronegativity value is for sulfur. So the order is oxygen greater than n nitrogen, nitrogen greater than sulfur. So oxygen contains more electronegativity. So electronegativity means it is the capacity, or it is the property of the atom or element to withdraw or to pull the bond electron towards that particular atom. If electronegativity is more, then it has a high capacity to withdraw bond electron towards that particular atom. So here, due to the more electronegativity of oxygen atom in furan, the delocalization of the lone pair of oxygen atom into the ring structure generally very less when compared to nitrogen, where it is somewhat less than that of the thiophene. That is, the order of delocalization of lone pair of electrons from the heteroatom is generally it is sulfur greater than nitrogen greater than oxygen. That is, sulfur heteroatom lone pair generally delocalizes into the ring system very fastly due to the less electronegativity than that of the nitrogen. In turn, the nitrogen lone pair easily delocalizes into the ring structure than the oxygen lone pair. It is due to the difference in their electronegativity values. More electronegativity means it is less delocalization. Less electronegativity means more delocalization. So delocalization in sulfur is more. Delocalization of lone pair in furan is very less. The pyrrole is intermediate in between the thiophene and furan. So due to this electronegativity difference values, their resonance values also changes. That's why the thiophene contains more resonance energy than that of the pyrrole. In turn, the pyrrole contains more resonance energy value than that of the furon. This is about the resonance energies and reason for variation in their resonance energies values. Okay, next, due to aromatic nature, due to aromatic nature, even though they contain conjugated pi systems or pi bonds in their structure, they don't undergo electrophilic addition reaction. Instead, they undergo electrophilic substitution reaction due to their to retain their aromaticity nature, and they undergo substitution reaction, but they don't undergo addition. If they undergo addition reactions, just like unsaturated compound, all just like alkenes, alkyne, they loses their resonance energy. So in order to retain their resonance energy, just like in the case of aromatic compound, just like in the case of benzene, even though it contains conjugated pi bonds, here also the five-membered heterocyclic compounds, even though they contains unsaturated bonds, that is five bonds, they don't undergo electrophilic addition, but they undergo electrophilic substitution in order to retain their resonance energy values. Okay. If you observe the resonating structures of furon, thiophene, and pyrrole, here the first one is resonance structures for pyrrole. Here, due to the delocalization of lone pair of electron into ring structure, we get negative charge. Here, this negative charge shifted further, then we get negative charge here. This negative charge shifted, then we get this structure. This is undergo further resonance structure to form this one. Here also sulfur undergoes same type of resonance or same type of delocalization of lone pair of electron into the ring system. So the case of thiophene also we get different resonance structures like this. In the case of pyrrole also, the lone pair of nitrogen atom undergo delocalization into the ring structure, then we get these resonating structures for pyrrole. If you observe all the resonating structures of five-membered heterocyclic compounds, the ring carbons generally contains negative charge, while the heteroatoms heteroatoms contains positive charge in all the resonating structures. So these all five-membered heterocyclic compounds are, they contains electron surplus carbon atoms in their ring structures and electron deficient heteroatoms. So due to the electron surplus in the ring structure or in the ring carbon atoms, their reactivity towards the electron deficient atoms, that species, that is towards the electrophiles, their reactivity is more when compared to benzene. Okay, this is all about the aromaticity and resonance structures of the five-membered heterocyclic compounds. Next, electrophilic substitution in five-membered heterocyclic compounds. As we discussed in the previous slide, due to the delocalization of lone pair of heteroatom into the ring structure, into the five-membered ring structure, the five-membered heterocyclic compound gets different resonance structures. In these different resonance structures, all the four ring carbons generally contains negative charge. Generally, it is mainly at 2 and 4 positions. Mainly, ring carbons contains negative charge, and the heteroatom gets positive charge. So, due to the electron surplus on the ring carbons, they easily undergo electrophilic substitution reaction. Instead, they don't undergo electrophilic addition reactions. So their reactivity is generally more than that of the higher than that of the benzene towards electrophiles. It is due to the electrons surplus on the ring carbon atoms. Here the electrophilic substitution generally mainly takes place at C2 position. Here in the case of 5-membered heterocyclic compounds, according to nomenclature or according to numbering, the C2 and C5 position are same. C2 C5 carbons are same, that is alpha alpha dash, or C2 C5 are same, as well as C3 and C4 are similar. So in the case of electrophilic substitution, the electrophile mainly undergo attack at C2 or C5 position instead C3 C4 position, because if you observe the reason why the electrophilic substitution occur at C2 or C5 position than that of the C3 or C4 position, the main reason is explained in this figure. Here the electrophilic substitution, if they observe the 5-membered heterocyclic compound, it is 5-membered heterocyclic compound. Here X may be NH. If X is NH, it is pyrrole. If X is equal to oxygen, it is furan. If X is equal to sulfur, it is thiophene. So here the heteroatom gets first number, next second, third, fourth, fifth, or alpha alpha dash, beta beta dash. Okay, this is numbering according to Arabic or Greek letters. In all the 5-membered heterocyclic compounds, here C2 equal to C5 or C3 equal to C4. So the incoming electrophile may attack on C2 position or C3, that is C5 or C4 position. They are similar. So there are two chances to incoming nucleophile to attack on the heterocyclic ring, that is it may be C2 or C5, or it may be C3, which is nothing but C4. So that is if the electrophile may attack at C2 position or it may be C3 position. There are two chances. Here the product yield generally depends whether we get two substituted product or whether we get three substituted product. Generally depends on the stability of the intermediate during the electrophilic substitution. If you observe the stability of intermediate during the electrophilic substitution at C2 position and at C3 position, during the attack at C2 position we get three resonance structures for the intermediate ion. Here it is more stable, it contributes more percentage toward the resonance hybrid. In the case of C3 attack, we get only two resonance structures. For any molecule, if the number of resonance structures are high, then the stability of that compound or molecule is high. So if the electrophile attack at C2 position, we get three resonance structures, so the intermediate is more stable. If the electrophile attack at C3 position, it gets only two resonance structures, so it is unstable when compared to C2 attack. So the electrophile mainly attacks at C2 position instead C3 position. So we get C2 substituted product as a major product during the electrophilic substitution of all 5-membered heterocyclic compounds. It may be furan, or it may be pyrrole, or it may be thiophene. In all the three heterocyclic 5-membered heterocyclic compounds, the electrophile mainly attacks at C2 position or C5 position. They don't undergo attack easily at C3 or C4 position. Okay, fine. This is all about electrophilic substitution of 5-membered heterocyclic compounds. Next one is pyrrole. The first one is pyrrole. Here it is pyrrole. The structure is pyrrole. According to IUPAC nomenclature, the pyrrole name is, it is azole. Azole indicates heteroatom. Ole indicates the ring size, that is 5-membered ring. Orally the name is azole, or it is azole, or it commonly known as pyrrole. Here it is pyrrole is one of the five-membered heterocyclic compounds with nitrogen heteroatom. Generally, it presents in so many natural products, as we discussed in the importance of heterocyclic compounds. It generally presents in hemoglobin, chlorophyll, and many other porphyrin rings. That is, generally the porphyrin rings is tetrapyrrole rings. So chlorophyll, hemoglobin are constituted with porphyrin rings. So in all the porphyrin rings, pyrrole structure is generally observed. Generally, it forms 6 electron or 6 pi electron aromatic sextet above the ring and below the ring. So it is due to the delocalization of lone pair of nitrogen heteroatom. Nitrogen heteroatom. So it forms 6 pi electron aromatic sextet. That's why it obey the Huckel rule, that is 4n plus 2 pi rule, and shows aromatic character with with resonance energy value 22 kilocalorie per mole. Pyrrole generally shows different or various resonance structures due to the delocalization of nitrogen lone pair of electrons, as we discussed in the earlier slide. So, due to the delocalization of nitrogen electrons of lone pair electrons into the ring system, we get these different resonance structures. All in these resonance structures, the ring carbons generally gets negative charge. They are surplus. The four carbon atoms are generally electron surplus. The nitrogen heteroatom gets positive charge. So it is electron deficient. Next one, it is introduction about pyrrole or azole. Next one is preparation methods of pyrrole. Generally, pyrrole is obtained commercially from distillation of coal tar. What is obtained from the distillation of coal tar. We can also synthesize or we can also prepare pyrrole through laboratory methods by using various methods. Okay. Next, what are the laboratory methods generally useful to prepare pyrrole? The first one is from acetylene. Acetylene is nothing but it is alkyne. The starting alkyne C2H2 formula. Treating acetylene with ammonia in the presence of red hot tube, we get pyrrole. That is, two molecules of acetylene undergo reaction with one molecule of ammonia in the presence of red hot copper tube and produces corresponding pyrrole compound. The other one is preparation from succinamide. It is succinamide. It generally succinic acid amide derivative. Succinamide is it is amide of succinic acid. Here succinic acid is generally one type of dicarboxylic acid. Here there are mainly major dicarboxylic acid is oxalic acid, malonic acid, succinic, glutaric, adipic acid. We can simply remember all these five dicarboxylic acid by using a mnemonic, that is O means such goodable. O means oxalic, M my means malonic, such succinic, good glutaric, apple A adipic acid. Okay, here succinamide is it is amide derivative of succinic acid. Treating the succinamide with zinc dust or distillation of succinamide over zinc dust, we can get pyrrole. That is distillation of succinamide over zinc dust, we get pyrrole. Okay, fine. Next, preparation of pyrrole from furan. We can also prepare pyrrole heterocyclic compound from the other five-membered heterocyclic compound, that is from furan. Treating furan with ammonia in the presence of steam and in the presence of a catalyst, that is aluminum catalyst, we get we get pyrrole. That is treatment of furan ammonia mixture with steam over alumina catalyst, we get pyrrole compound or pyrrole molecule. Okay, the next preparation method is polymer synthesis. Polymer synthesis, or it is preparation of pyrrole from 1, 4 dicarbonyl compounds. The name, it is named reaction based on the scientist who found the reaction. That is, it is polymer synthesis. Here, generally, the carbonyl compound, that is 1, 4 dicarbonyl compounds, which have at least one alpha hydrogens, they exist in ketoenol tautomerism or in the form of ketoenol tautomers. So, here, in the case of 1, 4 dicarbonyl compounds, generally the enol form proportion is very high due to the formation of hydrogen bonding within the molecule or intramolecular hydrogen bonding. So the proportion of enol form is very high compared to keto form. So this enol form easily undergo reaction with ammonia or amines to form corresponding pyrrole or substituted pyrrole derivatives. Here, for example, it is 1, 4 dicarbonyl compound. It undergo tautomerism, that is, it forms enol form. It is keto form. It is the second one is enol form. It is keto-enol tautomerism. This enol form undergo reaction with ammonia or amine. It is primary amine to form corresponding pyrrole or pyrrole derivative. Generally, the reaction, if you observe the mechanism, here the ammonia or amine, generally it is a base, acts as nucleophile, so it undergo nucleophilic attack on carbonyl carbon. Then we get this product. Here the nitrogen undergo further intramolecular nucleophilic attack on the other carbon atom. Then it produces this product, addition product. This addition product loses 2 moles of water molecule to form corresponding pyrrole derivative. This is a mechanism for preparation of pyrrole from 1, 4 dicarbonyl compounds. Okay, fine. Next, physical properties of pyrrole. Generally, pyrrole is a colorless volatile liquid. It is easily evaporates at room temperature. That is colorless liquid at room temperature. It becomes dark when it exposed to atmosphere air. So it is purified by distillation process during its use. When we want to use this pyrrole, we have to purify it by distillation method, because on exposure to atmospheric air it becomes dark. So we have to purify it before its use. Here, if you observe the smell of the pyrrole, it has a nutty smell. Generally, the smell is generally somewhat unpleasant smell. Next, it is a 5-member heterocyclic compound with aromatic character like furan and thiophene. That is, it shows aromatic character. It has some dipole moment. Generally, it is 1.58 device. Dipole moment is due to the delocalization of lone pair of nitrogen atom into the ring system. Nitrogen gets positive charge and the ring carbons gets negative charge. So the dipole direction generally from nitrogen heteroatom to towards the ring carbons. Next, generally pyrrole is amphoteric in nature. That is, it reacts with acids as well as it reacts with bases. That is, it is acts as a weak acid and weak base. If you observe the solubility, it's soluble sparingly in water. That is, solubility in water is generally very less, but it soluble in all organic solvents. That is, it completely soluble in all organic solvents, but it is partially or sparingly soluble in water. Okay, fine. Next, chemical properties of the pyrrole. Here, due to the aromatic character of pyrrole, it does not undergo any electrophilic addition, but instead it undergo electrophilic substitution reaction as in the case of benzene. Here, if you observe the reactivity of the pyrrole, it is more than that of the benzene because it is contains surplus carbon atoms in its ring structure. So it is more reactive than the benzene. So as we discussed in the previous slides, generally the electrophilic substitution takes place at all four positions, that is at C2 and C5 positions, instead C3, C4 positions. Here, in the presence of acid media, generally the pyrrole or all the 5-membered heterocyclic compounds generally undergo polymerization in the presence of acid media. So, many electrophilic agents or reagents which are used in the benzene chemistry or benzene electrophilic substitution reaction, we don't use such electrophilic reagents which are applicable to benzene chemistry in the case of pyrrole chemistry, because pyrrole undergo polymerization in the presence of acid media. Next, pyrrole generally reacts easily with so many electrophile, that is so many electrophilic agents or reagents such as nitrating agents. Here in the case of nitrating agent, here we should use mixture of nitric acid and acetic anhydride. In the case of sulfonating agents, we should use pyridine plus sulfur dioxide or sulfuric acid mixture. For halogenating nation, we should use in chlorosuccinamide or in bromosuccinamide or sulfuryl chloride. But here in the case of halogenations, if you treat the pyrrole with directly with halogen molecule, then the pyrrole ring undergo dissociation or breakage of the pyrrole ring takes place. Then the reaction is very violent with the halogen molecule. So generally in most of the cases, during the halogenation, we get polyhalogenated pyrrole derivatives. Okay, next. Next, amphoteric nature of pyrrole. That is, pyrrole acts as a weak base as well as weak acid. That is, it shows amphoteric nature. So here, if you observe the pyrrole structure, it resembles generally a secondary amine structure. Primary amine formula is RNH2. Secondary amine R2NH. Here it is NH. Here it is other or hydrocarbon part. That is, it resembles secondary amine structure, but it is not much more basic like that of secondary base or secondary amine. It is not more basic similar to that of secondary amine, though it resembles secondary amine structure. It is due to the delocalization of lone pair of electrons, nitrogen electrons into ring system. The availability of lone pair towards the electron deficient species or electrophiles is very less when compared to normal secondary amine. So due to the less availability of lone pair of electrons, it shows or it acts as a weak base, though it resembles the secondary amine structure. Here it is main region is delocalization of lone pair of electron into ring system. Here the basic character of amines is depends on the availability of lone pair of lone pair of nitrogen atom towards the incoming electron deficient species. So due to this delocalization of lone pair of nitrogen into ring system, the availability is very less, so it acts as a weak base. Generally, due to this delocalization of lone pair of electrons into ring system, we get positive charge on the nitrogen atom and negative charge on the ring carbons. Okay, fine. This is delocalization. If the lone pair of nitrogen atom reacts with the electron deficient species such as proton, then it forms corresponding pyrrolinium ion. Pyrrole reacts with proton to form pyrrolinium ion. Here pyrrole shows aromatic character, but pyrrolinium ion don't shows any aromatic character. It don't obey 4 n plus 2 5 electron rule or Ockel rule. So the pyrrole is aromatic in nature, but pyrrolinium ion is non-aromatic. So it shows less basicity because the intermediate formed in the basic character generally non-aromatic. So it shows less basicity. Next, if pyrrole acts as weak acid, here pyrrole also acts as a weak acid because due to the delocalization of lone pair of nitrogen electrons into ring system, the nitrogen gets positive charge as we discussed in the earlier slide or in the resonance structures of pyrrole. So nitrogen gets positive charge and carbon atom gets negative charge. Okay, fine. Due to the positive charge on the nitrogen atom, that is nitrogen generally basically more electronegative atom. Then to reduce this positive charge on the nitrogen atom, it attracts the NH bond electrons. NH bond electrons. Then the NH bond becomes weak. So in the presence of base, or in the presence of strong base, the NH hydrogen easily removes as proton. So the pyrrole shows acidic character by losing NH hydrogen in the form of proton to bases and forms a stable pyrrole anion. Okay, I will discuss about this pyrrole anion in the next slide. Okay, fine. Next, here if you observe the resonance structures of the pyrrole and resonance structures of the pyrrole anion. Generally, here pyrrole anion, that is the anion which is obtained due to the loss of NH hydrogen, is generally known as pyrrole anion. This one, pyrrole anion is more stable than the pyrrole because if you observe the pyrrole resonance structures, we get different resonance structure due to the delocalization of lone pair of nitrogen atom. In all these resonance structures, there is charge separation. That is, there are two charges in the ring system. Positive charge on the nitrogen atom, negative charge on the carbon atom. So due to this charge separation, their contribution, that is the contribution of those canonical structure toward the resonance hybrid, is very less. So pyrrole is somewhat unstable when compared to this pyrrole anion. Here if the pyrrole loses this proton to the base, then we get pyrrole anion. This pyrrole anion is more stable because in these resonance structures there is no charge separation, only negative charge delocalizing on all the ring atoms, so it is more stable. That is, pyrrole anion is more stable than the pyrrole. It is generally similar to that of the phenol. That is, phenoxide is more stable than that of the phenol. Here also pyrrole anion is more stable than that of the pyrrole. So as pyrrole resembles the acidic property similar to that of phenol, pyrrole also resembles some chemical properties which are exhibited by phenol due to this resemblance in the acidic property. Okay, fine. Next, if you observe the chemical reactions of pyrrole, here if you observe the electrophilic substitution reaction, here there are two positions available per incoming electrophile as we discussed in the previous slides. They are C2 or C5, both are same. The next one is C3, C4 position. C2, C5 or C3, C4 position. So the electrophile, for example, here H plus may undergo attack at third position to form 3H pyrrolinium ion, or it may undergo at second position to form 2H pyrrolinium ion. So there are majorly two chances, but the major product is two substituted product because the stability of intermediate. So that the electrophilic substitution of pyrrole. In the case of nitration, generally for nitration of pyrrole, we use, in the case of electrophilic substitution reaction of pyrrole, we use generally mild agents because of more reactivity of pyrrole, or more reactive of all five-membered rings. We should use mild agents for electrophilic substitution reactions. Here also, instead of taking concentrated nitric acid, concentrated H2SO4 mixture, that is nitration mixture, we should take mild agent, nitrating agent, that is mixture of acetic acid and nitric acid, which forms nitroacetate. This nitroacetate liberate nitronium ion electrophile. This nitronium ion electrophile attack at C2 position of pyrrole to form 2 nitro 1H pyrrole. For sulfonation, the sulfonating agent in the case of pyrrole is sulfur trioxide and pyridine mixture instead of taking concentrated sulfuric acid, because in the presence of concentrated sulfuric acid, pyrrole undergo polymerization. So we should use mild reagent, that is mixture of sulfur trioxide and pyridine. Then we get pyrrole to sulfonic acid. Here the reaction with halogens, for example reaction with chlorine, we get 2 chloro, but the product is very less. Generally the reaction, the direct reaction of pyrrole with halogens is explosive. The explosion of ring takes place, so we don't get majorly this type of products in halogenation. But in the case of a reaction of pyrrole with iodine, we get tetraiodopyrrole, tetraiodopyrrole, which is known as iodole instead of pyrrole, because all the hydrogens of pyrrole replaced by 4 hydrogens replaced by 4 iodine molecules, so it is named as iodole. So we get tetraiodopyrrole, which is nothing but iodole on reaction of pyrrole with iodine molecule. Acylation of pyrrole. Next one is acylation of pyrrole. For acylation, we may take acetic acid anhydride or acid chloride in the presence of Lewis acid, that is in the presence of boron trifluoride Lewis acid. Treating pyrrole with acetic anhydride, we get 2 acetyl pyrrole. Okay, this is some electrophilic substitution of pyrrole. Next, reduction of pyrrole. Here the pyrrole may undergo reduction to form various reducing products in the presence of various reducing agents. If you treat pyrrole with zinc and acetic acid mixture, that is reducing agent, it acts as reducing, that is metal plus acid. Then the pyrrole undergo reduction to form 2,5. Here the saturated position is 2 and 5, so 2,5 dihydropyrrole, that is partial reduction of pyrrole takes place in the presence of acetic acid and zinc mixture. If you treat pyrrole with metal and hydrogen gas, that is nickel, palladium or platinum metal, in the presence of hydrogen gas, we get completely reduced product, that is tetrahydro, that is 2,3,4,5 tetrahydropyrrole, or which is commonly known as pyrrolidine. That is catalytic, in the presence of catalytic hydrogenation, we get complete reduction of pyrrole to form or to get pyrrolidine. But in the presence of zinc acetic acid mixture, we get partial reduced product, that is dihydro product. Okay, next one is Remer-Timmer reaction. Here, due to the resemblance of pyrrole acidic nature with phenol acidic properties, here pyrrole also undergo some chemical reactions which are exhibited by phenol. That is, phenol show exhibit trimer reaction. Here also pyrrole exhibits Remer-Tiemer reaction. In the Remer-Tiemer reaction, pyrrole undergo reaction with chloroform in the presence of base. Due to the reaction of chloroform and base, they produces dichlorocarbon, which is nothing but an electrophile in this reaction. This electrophile undergo attack at C2 position. This dichloro addition product may undergo hydrolysis to form two various products. It may form pyrrole 2 carboldehyde, or it may form 3-chloropyridine due to the ring expansion. If the dichloropyrrole derivative addition product undergo ring expansion, then we get 3-chloropyridine. Without ring expansion, we get pyrrole 2 carboldehyde products. Okay, fine. Next, there are some substitution reactions of pyrrole at nitrogen atom. Here, substitution generally, that is replacement of nitrogen NH hydrogen, replacement of NH hydrogen with metal. It is nothing but metallation of pyrrole. That is, if the hydrogen is replaced by metal, then it is known as metallation. So here, if you observe the metallation of pyrrole reactions, the first one is pyrrole undergo reaction with strong base, that is, it may be sodamide or potassium amide, or with liquid ammonia, or it may undergo reaction with sodium or potassium metal. Then we get pyrrole sodium or pyrrole metal salt, potassium or sodium salt. Generally, it is ionic compound, salt-like structure. If the pyrrole undergo reaction with Grignard reagent, for example, ethyl magnesium bromide, then we get the metallated product as a covalent product. Here also pyrrole undergo reaction with alkyl lithium compounds, that is super Grignard reagents, to form N-lithium derivatives, which is also a covalent compound. Okay, these are example for metallation of pyrrole, that is substitution of NH hydrogen with metal atom. Okay, fine. Next, if you summarize all the chemical properties or chemical reactions of pyrrole, that is, if you observe the chemical reaction one by one, here the pyrrole generally in the case of chemical reactions of pyrrole, we use generally mild reagents because more reactivity of pyrrole. In the case of electrophilic substitution, generally it undergo substitution at second position. It is more stable. In the case of reaction of pyrrole with iodine, we get tetraiode of pyrrole, which is nothing but iodole. In the case of nitration of pyrrole, we get 2-nitro derivative. Here the nitrating agent is mixture of nitric acid and acetic anhydride. In the case of sulfonation, that is, the pyrrole undergoes sulfonation with sulfur trioxide and pyridine mixture, or in some cases reaction with sulfuric acid and pyridine solvent. Then we get pyrrole 2 sulfonic acid. Reaction of pyrrole with alkyl halide, in the presence of Lewis acid catalyst, we get 2 alkyl product. If you treat pyrrole with acid HCl, we get pyrrolinium chloride. If you treat pyrrole with base, we get pyrryl anion, that is corresponding metallated product. If you treat pyrrole with alkyl halide without using Lewis acid catalyst, then alkylation takes place at nitrogen atom instead of taking at C2 position. If you use Lewis acid catalyst during the alkylation takes place at C2 position. Okay, during the acylation, we get N-acyl derivative. If you use Lewis agent, then acylation takes place at C2 position. Without Lewis agent, then N acylation. Without Lewis agent, N alkylation. Okay. Treatment of pyrrole with nitric acid, we get N nitroso derivative. Treatment of pyrrole with Grignard reagent, we get methylated product, that is hydrogen is replaced by MgX, and we get ORH hydrocarbon, that is it is useful to prepare hydrocarbon. Okay, fine. Next, other chemical reaction of pyrrole. Here, if you treat pyrrole with phosphorus oxychloride in the presence of DMF, that is dimethyl formamide, we get pyrrole 2 aldehyde CHO. CHO group, formal group is substituted second position. That is generally known as a named reaction, that is Wills-Meyer reaction. If you treat pyrrole with acid halide, that is acid chloride, in the presence of catalyst, Lewis acid catalyst, then acylation takes place at second position. Without catalyst, acylation or alkylation generally takes place at nitrogen atom. In the presence of catalyst, alkylation and acylation takes place at C2 position. Okay, fine. If you treat pyrrole with methylene diiodide, then we get corresponding pyridine compound. If you treat pyrrole with chloroform in the presence of ethoxide, we get 3-chloropyridine as a major product. But treating of pyrrole with chloroform, the presence of base, we get mixture, that is pyrrole 2 carbaldehyde and pyridine 3-chloropyridine, mixture of products. But in the presence of ethoxide, we get only 3-chloropyridine. Okay. Oxidation of pyrrole in the presence of chromic oxide, we get this oxidized product, that is pyrrole 2,5 dione product. Reduction of pyrrole in the presence of metal and hydrogen gas, complete reduction takes place, we get pyrrolidine product, that is tetrahydro product. In the case of partial reduction, that is reduction with zinc and acetic acid mixture, partial reduction takes place and we get dihydro, that is 2,5 dihydro product. If you treat pyrrole with chloroform, carbon tetrachloride and alkali compound, then we get pyrrole 2 carboxylic acid, as in the case of phenol Riemann reaction. Okay, these two are Riemann reactions. If you treat pyrrole with carbon dioxide in the presence of base, we get pyrrole 2 carboxylic acid. If you treat pyrrole with mixture of hydrogen cyanide and hydrogen chloride in the presence of Lewis acid catalyst, that is zinc chloride, followed by hydrolysis, we get pyrrole 2 carbaldehyde. It is a named reaction, that is it is Goterman reaction. Goterman reaction. If you treat pyrrole with carbon monoxide and HCl mixture in the presence of Lewis acid catalyst, we also get the same product as in the case of Goterman reaction, that is pyrrole 2 carbaldehyde. It is nothing but Goterman-Koch reaction. That is by replacing a hydrogen cyanide, which is used in the Goterman reaction, with carbon dioxide, it is known as Goterman-Koch carbon monoxide. Okay. If you treat pyrrole with alkyl cyanide, instead of taking hydrogen cyanide, mixture of alkyl cyanide and hydrogen chloride, the presence of Lewis acid catalyst zinc chloride, followed by hydrolysis, we get acylated product. It is modified Goterman reaction. In the case of Goterman, we take hydrogen cyanide. In case of Goterman-Koch, we replace hydrogen cyanide with carbon monoxide. Here, in the case of Hauben-Hosch reaction, we replace hydrogen cyanide with alkyl cyanide. Then we get acylating product, that is ketone, 2 keto derivative. Okay, if you treat phenol with formaldehyde and an amine base, it may be ammonia or any alkyl amine which contains at least one NH bond or at least one hydrogen on nitrogen atom. Then we get an managed base. It is similar to that of phenol reaction. Oh, sorry, it is similar to that of reaction of as active acid compound with formaldehyde and amine to form a managed product. Okay, here pyrrole acts as a active compound, active or acidic compound in the managed reaction. So it forms managed base. Pyrrole also undergo reaction with diazonium salts to form coupling products. That is, diazo coupling reactions also take place with pyrrole as in the case of phenols to form corresponding coupling products. This is all about chemical reactions of phenols. Okay, fine. Next. Thank you very much for your patience and for watching this video. Thank you one and all. Okay, bye.